We are now going to do exciting things.
I am very excited.
We are
Well, I
going-
was telling them how I'm coming home on Tuesday.
How are you? Yay. What time?
Well, I'm driving, so I'm trying to figure out if I'm gonna do class from in the car or wait. I'll probably do class from here and then drive after.
Well, that's exciting. Are you going to be home for good then?
Yeah.
Through Christmas, that's the end.
Yeah.
Okay, well, let us start. Sorry, I'm just a little bit late this morning. I had to get coffee and I did a late walk, so. It's so nice out here. Have you been outside, guys?
I'm waiting till it's
Yeah.
65.
It's beautiful outside.
No.
Okay, so
Enjoy it while it lasts.
now this is going to be exciting because I don't really know what I'm doing here. This is old stuff. But what I like about this is that I used to do this a long time ago, and I feel a whole lot more confident. Just so you guys know, I know what it's like not to know this stuff, and you're not going to be adequate at it unless you work at it really hard, and it'll take you some time to do it. But I have confidence. How you doing, James?
Doing all right. Just chilling here.
Missing Mike. Mike, I hope you're listening to the recording of this. Let me get out my Epic pen, and we're going to go to
Pen.
Blackboard. Okay, so we are going to look at a system. What's your favorite color against the background?
I prefer a white background.
Oh, I
Background.
like the black. I'm taking what color? I like black. That's just so cool to me. I think they're like cool colors. I'm big into colors though. I'm going to use this dark blue. Just set this up. So what I'm going to do is I'm going to take an arc, and I'm going to take an arc here. Okay. And what we're saying is this is all part of. Oh my gosh, how do I do this? Oh, that's close. Actually, you know what? I guess I should do it this way. Should draw the circle first. That's about the middle, right?
Not enough coffee.
Well, I got plenty of coffee. I'm just not sure how to draw this diagram. Okay, so I've got this. And what I have got going on is that this thing is rotating. Okay, it's rotating at a frequency little omega. Okay, this distance is r, radius, obviously, and this amount in here is going to be delta theta. Okay, so in other words, I've got an object that is going to be rotating around the outside of this circle. It has a radius of r. It is going to go through an angle, which we're going to call delta theta. So if you think that an angle is theta, and then another angle is theta, and then this is the change in theta. Now, each one of these things will have a vector tangent to the curve. Okay? And what is that vector going to be called? That's the what vector? That's the velocity vector.
Angular velocity.
Okay, so because it's at a tangent, we are going to say that the tangent is the same in both of these. Now, here's the question that I have for you. What do you know about the magnitude of those two vectors?
They should be equivalent if it's constant velocity.
Right? They should be the same. It's going at a constant rate, angular velocity around the circle. These are going to be the same magnitude, but they're going to be slightly different. So what I'm going to do is I'm going to redraw this vector over here as a light blue. I'm going to kind of keep it so that you see that it's yellow. And I'm going to say that that vector is this vector. Okay? So what I'm saying is that this vector and this vector are the same vector. I just put them at two different places.
So you're not adding them? They're just, the second one is randomly?
I'm moving this vector, watch, I'm moving this vector to this location so that the two vectors have the same endpoint.
Oh, I see what you're saying. Okay, gotcha.
And what that means for me is that this, well, it didn't quite come out the way I wanted it to. This vector here is what vector is this? What do we call that vector?
Acceleration.
Well, yeah, it's the change of velocity vector. So that means that this vector, yellow, is v plus delta v. And then what I'm going to do is I'm going to erase this version of it to say that, notice it's the same magnitude, but it's a little bit different. So there is a change. Now, I want you to make delta v, for James' sake, because he's right. That's a hard letter to draw, isn't it? It's going to make this, as it goes to 0, what will this become?
What will what become?
What will delta v vector become if it goes to 0?
Constant, no acceleration. The
No,
acceleration.
no. What I'm saying is that this gets infinitely small, the angle infinitely small, so that this becomes infinitely small. So what does delta v vector become?
Becomes delta v.
Mm-hmm. So if delta v becomes infinitely small, that's what a derivative does. It goes to dv. Okay, so the acceleration is going to be equal to this delta v vector over a change in time, or we could say dv dt is going to give you acceleration vector. Now, let's redraw. I'm going to redraw this triangle over here, okay? So I'm going to redraw this triangle. I'll use the same colors over here. So, but I'm going to make it a little bit bigger. Okay? So do you understand what I'm doing here? I'm just drawing this to be a little bit bigger. What is this angle? What's that angle?
Sine.
No.
No.
Just give me the value of this. Look at the picture and tell me how big is that angle?
Del theta.
Right? It's delta theta.
Theta.
Which you could also say as d theta if the angle goes to 0. Now, is this a right triangle?
No, not necessarily.
Well, no, absolutely.
No, it can't. No, it can't be.
No.
Because this, the hypotenuse, if this were a right triangle, because it kind of looks like a right triangle, the hypotenuse can't be the same side as this side. But let's imagine if it were, oh, that's horrible writing. If it were a right triangle, then what is the length of the blue? Remember, what do we have to remember? We have to remember SOHCAHTOA, right? And so we know, let's say that we know the hypotenuse. The sine of the angle is the,
Opposite of
I'm sorry, the cosine, no, I want to know the size of this pink. The sine of the angle is the opposite over the hypotenuse.
Right.
So that the pink sine of theta equals opposite. I have to think this up. Sine of theta is equal to the opposite
over hypotenuse.
over hypotenuse. Okay, so that the sine of the angle is equal to the opposite, which is delta v, over the hypotenuse, which is v. These are all vectors, so I'm going to take the magnitude of it.
Okay, so what's the purpose of assuming it's a right triangle other than for
Okay,
the
so do
simplicity?
you agree that I would have to take the sine of this angle rather than just the angle to actually calculate this?
Yes.
But sine of theta is approximately equal to theta. Do you remember this? I think we told this once before. When theta is much less than 1, if it's very small. So right now, don't forget that we're using not degrees, but we're using radians. So somebody take your calculator and do pi divided by 100. Or actually do pi divided by 180. That's like 1 degree. What's the value of that? So I'm going to put it up here. Example, pi over 180, which is really 1 degree. What is pi divided by 180?
I got 0.017.
0.017. Okay, that's this. Okay, what's the sine using radians of 0.017? But you have to put it in radians. What did you guys get?
1.699 to the minus second.
0.11699. Do you agree that is just about the same?
Yep.
So what we're saying then, from this fact, and remember, we're talking about, this is only true when the angle is very small. So I'm saying that this is approaching 0. So that means these are about the same thing. So that means what this ends up saying is that the the magnitude of this delta V vector is equal to the magnitude of the velocity vector times d theta. Does that make sense to you? That's the magnitude. Now, if I say that I want the derivative, oops, sorry. Let me do this just so can I erase this? Does anybody have a question as to what I mean by this?
I got that one down.
So, and that, see, this is the kind of thing that's just a little mathematical trick. So I'm looking at if this is the change in the velocity, right, with respect to time. So the change in the velocity vector with respect to time, oops, is going to be equal to the velocity vector magnitude times d theta, oops, no, delta theta over delta t, if this is all magnitude.
So you just divide
All I did was
both
divide
sides
both sides
by
by delta t. Okay, now let's do this instead. Let's put it in a derivative form. dv dt equals the magnitude of the velocity times d theta dt. Does that make sense?
Mm-hmm.
Here's the question, though, for you. The left side is a vector. The vector points according to this pink vector over here. I'm making the magnitude of the velocity vector, but I need to make it point in a direction. Which way would this delta V vector point if delta theta went to d theta? In other words, it became infinitely small. It makes a right triangle, right? If I said this angle gets really small, it's like it's a right triangle. In fact, it is a right triangle if it's 0, right? You can think of that as a right triangle if it's 0, or as it approaches 0. Do you see that it would point perpendicular to the velocity vector? But it's pointing perpendicular to the tangent vector, because the velocity is tangent, which means the change in the velocity is pointing toward the center. It's a centripetal force.
Oh, yeah.
It points
yeah.
toward the center. So what I would do is I'm going to multiply this times the vector r divided by r. Now, this is kind of a funky thing. Do you understand what I've done here? I've taken a vector of the radius and I divided it by the magnitude of the radius. So what have I put in there? What is the thing in the parentheses? What do we call the thing in the parentheses?
Unit vector?
Say what?
Unit vector?
Correct. That's a unit vector. Now, which way does that unit vector have to point? So we're basically saying here that the vector points along the radius, which is this way. But which way does this pink have to point?
Towards the interior of the
Towards
circle.
the center point.
It needs to be the middle, so I put in a negative r. I put a negative in there. So what I'm saying is I'm making this now a vector with that magnitude. But what is the speed? Isn't it just the frequency times the radius? That's how fast I'm going. The larger the radius, the faster this thing has to go because it makes it around in a certain amount of time. So this is This is like radians per second would be the frequency times meters. Now I have a velocity of meters per second. So that means that dv dt equals omega times r times d theta dt times negative r vector divided by r. But what happens to the r's?
You cancel.
This cancels out, and what am I left with? And for the sake of simplicity, I'm going to go dv dt, the vectorial acceleration, is equal to minus omega squared times r.
Okay, where did the other?
Because what is d theta dt?
That's the
Isn't
angular
that,
velocity.
right? Isn't this
Yeah.
is omega? So it's the angular change, the change in the radians over time. So I get dv dt equals minus omega squared r. And which way does that point? It points toward the center. So we call this the centripetal force.
Huh.
But there's always a but, right? I want to show you something else that's kind of cool. So I'm going to get rid of this for a sec. Give me one more little thing here. Isn't that fun?
It is kind of cool.
All the things just equally equate each other. That's always something about math that's interesting. How many things actually are just equal to each other?
Equal to each other. So we said that omega, look over here, is, or omega times r is v, is the magnitude. So I'm just going to use v. So omega,
Oh,
It's a
omega
mega omega.
is equal to v. Now, notice I'm just going to go with v. I don't have to put the vector on and the magnitude signs because it's just a scalar, over r. But omega squared r, if the centripetal force is omega squared r negative, then it's also equal to v squared over r squared times r. But one of the r's cancels, and I get what? Equals v squared over r minus. But if I think of, what if I get rid of the minus sign? Make it positive. Then instead of the centripetal force pointing toward the center, I have a force pointing away from the center. And what do we call that?
centrifugal.
Centrifugal.
Centrifugal. Which is what we call the apparent force.
It's a pseudo force.
Because it's not really a force, right? It's not causing the acceleration. What's causing the acceleration is this thing must be tied to a string that's pulling it toward the center. But it appears to be opposite. So we lose the minus sign. The only difference is the direction that it points. But you see that v squared over r is omega squared times r. That is both the same, the magnitude is the centripetal acceleration. Does that make sense to you?
Yeah.
Okay. Are you guys ready to really freaking rock? Jacob, how you doing, buddy?
Hanging in there.
Do you guys have any questions on anything here that we've done?
Far so good.
Because I think, to me, this is actually all pretty good. I think I did a much better job with this. Do you understand the difference between going from the deltas to the d's? It's just, right, the difference between delta v and dv is that they go to zero. They're infinitely small. Okay, so let's go to this. Now let's see if I can draw. This is gonna be fun. This is
I
the
know.
Earth. This is the
I know.
Earth.
Oh, sorry.
Why is my sound is all garbly? Jim Norris, would you talk?
Testing 1, 2, 3, 4, 5.
I'm having a real problem with my sound system.
Your video is fine.
Now my speakers, what I'm hearing is not good. So hold on a sec. Hello? Talk again?
Testing 1, 2, 3, 4, 5.
Thank you. I just reset my sound card. Okay, so what is the rotation of this? What letter do I write?
Capital Omega?
Right? Yay. That's capital Omega, which is how much?
Oh, what was that?
2 pi per day. Right? 2 pi per day,
Mm-hmm.
which is, right? Do you know how many seconds would you calculate that to be? Well, if you went 24 hours and converted that to seconds, you would be wrong.
Like
And that's
23.
because we have what's known as, do you know what it's called? Type of day we have?
I know they mentioned it in the book.
Sidereal day. This is how long does it take the Earth to make a complete rotation? It's actually 23 hours, 56 minutes, and 42 seconds. That's how long it takes for the Earth to spin one complete rotation. Now, did I explain to you why that makes why we have a leap year? So, and why our day is 24 hours? So I want you to imagine that that you're at the Earth, and I'm the sun, I'm pointing directly at you. Or no, you're the sun, I'm the Earth. I'm pointing directly at the sun. It takes me 23 hours, 56 minutes if I were to do this and go all the way back to you. Does that make sense? So why do we call it 24 hours? Well, during that time, the Earth is orbiting the sun. So I'm moving. So after 23 hours and 56 minutes, I am now here. But the sun is over that way, you see? So it takes me a couple more minutes to get back to pointing right towards the sun. That's why we have 24-hour days, because if you were to take 3 minutes and 18 seconds and multiply it by 365, you're going to get a quarter of a day. So at the end of an entire orbit around, you're going to come back, and instead of being back to the sun, you're going to be off, pointing this way. You're a quarter of a rotation from being back. And you do that 4 times, and all of a sudden you lose a day. So you put another day to spin that back around, and that's why we have a leap year. And it's actually more complicated because it doesn't work out to be exact. So you have to really work out the mathematics, but it's an amazing thing, isn't it? It's an amazing concept. So what that ends up doing then is omega, if I put in this stuff, and you could do it yourself, I'm going to save you the time, is 86,164 seconds divided by 2 pi. So now take your calculator, and what do you get?
I get 0.00007288.
Really? Why is it 7.292?
That's what I got. I got 7.292 to the minus
Use
fifth.
pi or use 3.14?
I just used 3.14.
Yeah, I went out more.
So that one, that's the number you should get. So this is omega. So when we talk about 2 omega v sine phi, this is the omega we're using. That is the rotational frequency of the Earth. Which way does the force of the Earth rotate? As it rotates, there's an inward directed force. What is the centrifugal force of the Earth? Or centripetal, I should say. I'm going to forget about the minus sign. It's omega squared times the radius of the Earth. So go ahead and, well, oops. It shouldn't be that. It should be omega squared RE. So to calculate that,
So it's centrifugal force, not centrifugal, right? It's ifical force.
okay, listen. I'm writing the word century. When I write the word century, I don't care whether it's petal, which is toward the center, or fugal, which is away. But the word is not centrifugal. It's spelled centrifugal. It's pronounced centrifugal.
Centrifugal.
It would have been a whole lot smarter if we had said centrifugal. Because then you would go, it's easier to remember, it's easier to differentiate. But since I'm not caring right now, I know the direction that would be. So go ahead and calculate that out. And what's the radius of the Earth?
6.37 times 10 to the 6 meters.
Okay. Right, that's in the appendix of the book. That's a number you probably will memorize. It's certainly one that I memorized. 6.37 times 10 to 6. What do you get?
0.0339.
Scientific notation.
3.387 times 10 to the negative 2.
Oops. I just found out my aunt had a mini stroke. She seems to be okay. She's under doctor's care. Say it again.
3.387 times 10 to the negative 2.
What's the unit?
Newtons.
No.
Second squared.
Well, you have frequency, which is per second squared. But you have radius, which is meters.
Second squared.
So what is that the unit of?
Is that
Meters per second squared is the unit of what?
acceleration?
Okay, I know you would say acceleration, and you're not wrong, but that's not what I want you to say.
Newtons per kilogram.
Which makes it a what? That's the force.
Ergs?
You
So
said Newton
weight.
per kilogram, right? That's
Yeah.
and you see the mass in here?
No.
What value of mass are we giving it? How much is the mass? 1. If it's 1 kilogram,
Oh,
then the kilograms go away.
it's unit, man. It's, you know.
So this, even though you say this is an acceleration, it's easier if you think that this is a force per unit mass. And so we are always going to use the units meters per second squared when we talk about forces, because we're talking about force per unit mass. And then if we multiply the force per unit mass by the mass, then we get the actual force. Okay? So let's imagine that somebody is standing on the earth and they have a mass of 150 kilograms. What's their weight? Oh no, hold on, that would be really big. Hold on.
1470.
Let's do it this way. Let's make them. Let's have a mass of 50 kilograms. No. 20 kilograms. That's their mass. What's their weight? Well, weight is mass times what? Gravity. So their weight is actually 20 kilograms times 9.81 meters per second squared. So their weight is actually what? And I guess this is not a person. 20 kilograms is a pretty small person.
196.2.
196.2 what?
Kilograms meter per second squared.
Which is
It's just a Newton, right?
the Newton.
Yeah.
Right? That's what a Newton is. So the weight would be 196.2 Newton. But that's not really true, because their apparent weight, like the Earth is spinning around, and do you understand that there's an apparent outward directed force? That's the apparent force. So it's actually 20 kilograms times 9.81 meters per second squared minus 3.387 times 10 to the minus second meters per second squared. So that's 20 kilograms times what? What does this equal?
$128.46.
One.
Oh, inside, I did the whole thing.
Yeah.
6.423 inside
Okay,
the first.
no, you have something wrong. 10 to the minus 2, this is
Oh, 10 to my,
9.776.
9.776 meters per second squared, which then multiplied by 20.
195.523. Or 195.5.
Whatever. So do you understand that I actually weigh less because I'm on the Earth that's spinning?
But isn't there something where you weigh less at the equator and then you weigh more at the poles because you don't have that centrifugal?
Well, if I'm standing here, then I have the outward apparent force making me weigh less. If I'm standing here, do I have a force pointing up?
No.
Okay, now let's watch this for a second, as long as you brought that up, because that's a good point. What if I'm standing here? What if I'm standing there? And let's just say, for the sake of argument, that I'm standing because this is at the equator. So this is some degree of latitude. And what's that angle then?
Phi?
Right? We don't use theta for latitude, we use phi. So we're at some phi. And I'm telling you, it's so hard to it's so hard to draw a phi on the pad. There we go. That's some angle phi. So do you agree that the force that's going to be acting apparently is outward, or really the actual force is this force pointing what? Where's the force pointing?
Or the
Toward the what?
radius,
Well,
or
no. It's pointing toward the axis of rotation.
the axis of rotation.
So I would weigh a percentage less than what my normal mass is because I'm standing at a latitude. But how much less? What is the value of this force? What is the value of this force compared to this force? And forgive the drawing, it's not drawing the same scale. Actually, I suppose I could, right? I might as well do it right. Do you agree that force is going to be less than that force?
Mm-hmm.
Much less. Let's imagine this. I have this distance, r, of the Earth, and then the force will be this magnitude, 3.37. But over here, what's happened is that the radius of the Earth is less. The radius that I'm looking at. So I want you to imagine this, that what I'm doing is I'm looking at the top-down view of the Earth. And when I'm at 42 degrees latitude, which is where we are here, or whatever the degree latitude, I'm actually looking at a smaller circle. So I'm seeing the Earth spin around, but I'm making a smaller radius. So this radius here is what we call the apparent radius, which is what value? What value will that radius be?
Okay.
Yeah, go ahead.
Cosine of that angle, which should be phi.
Cosine. Because do you
Yeah,
agree?
the yellow lines are parallel, so those are complementary angles.
So this angle here, and you could look at it this way. Do you agree that that angle here is phi also?
Yeah.
Right? Congruent angles, or like you said, complementary angles, which you could also do. So if this is the case, then the radius of the Earth, which is RE, which is the red, then the adjacent side, so Ka, is that the radius, the apparent radius is equal to the Earth's radius times the cosine of the latitude. The hardest letter to draw on a computer. That's what it is. Now, playing with geometry, I could have used this angle and used the sine. So the sine, and this is just trig, the sine of an angle is equal to the cosine of the complement. That's when you start, I told you this before, people who struggle in calculus when they're taking class, probably they have bad trig. They don't remember the trigonometry. When you struggle in trig, what's the reason you struggle? You have bad algebra. Once you figure out algebra, then trig becomes easier. Once you get trig, then calculus becomes easier. But things like this, I mean, you do this all the time. You'd forget that that's
An identity.
an identity. Thank you. But then again, that's just geometry, knowing congruent angles. So you see how mathematics builds on itself, and you really got to know that. And it's fun because if you remember the geometry and angles and which are congruent and right triangles, and you're really good at that, you could always recreate most identities. You can figure that stuff out. So does that make sense that a person would weigh less at whatever this latitude is than a person at the North Pole, but you'd weigh more than a person on the equator? Now, is it a lot different? No, it's very small. But if you're doing rocket science, you better take that into consideration. So it's kind of funny because people might tell you, hey, I don't see why meteorology is so hard. It's not rocket science. Show them this page and you go, yes, it is. This is rocket science. What do you guys think about that? Let me go freshen up my coffee if you don't mind. So I'm assigning that problem, 7.16 over the weekend, deals with the parent graphite and a couple other things which we'll talk about. So get that done, okay? Let's go here. Anybody look at Zoom 5.0? Oh, more security enhancements. Any questions on this?
Nope.
Okay, let's try. I'm gonna keep this, so I'm gonna do some big erasers. clean up the board a little bit. Oh, I don't want to, no, I didn't want to get rid of that. I better go to a smaller guy to erase. Ah. I just don't want to have to redraw this picture. Does anybody have problems with any of that stuff?
No.
Okay. There, this makes me happier now. How you doing, James? How's your project? Hey guys, how's your project coming along while I'm doing this?
It's going all right. I didn't make too much progress last week due to some family medical issues that came up, unfortunately. Everybody's fine now, but I was pretty distracted last week.
Okay, well, I'm sorry to hear that. Okay, let's imagine this. Let's imagine that on the Earth, I have somebody at the equator traveling this direction. So if you can kind of think about that arrow going around. They're traveling on the equator toward the what direction? Which way are they traveling?
Going from west to east.
Okay, so they're traveling from west to the east, which means they're traveling in what velocity are they traveling?
Zonal? Is that what you're looking?
Yes, that's what I'm looking for. So what velocity would it be? What do I assign the velocity to be? U.
Oh, okay.
Right? I'm going to assign the velocity to be u. But what's my absolute speed? Is actually omega RE plus u. That's my velocity. This is in what we call an absolute reference. So I'm floating around in space and I'm looking at that object on the Earth. And I know that the object is moving around in a big circle in space, and it's moving at a velocity u, and they're going in the same direction. So my centripetal force or I could have said the centrifugal force. So I think I'm just going to go centri-force is v squared over RE. But what is that force? It's actually omega RE plus u squared all over RE. Super important here. You guys understand what I'm doing?
I'm sorry, can you say what that is again? The absolute
Radius of the Earth, dude. Radius of the Earth.
No,
Absolute reference.
reference. Okay. I couldn't read that.
Yeah. Absolute reference. In other words, I'm looking at an object moving on the Earth from outer space, looking down. Because on Earth, you're standing in the equator, you don't think you're moving, but you are. Right? You're spinning with the Earth. So this is the velocity, and then I'm squaring it to get this. Now, FOIL this. Go ahead and tell me what this equation equals.
That's the acceleration.
Well, no, FOIL it. you have a square of a sum. So use the FOIL method. No, not FOIL. Just expand this out. Actually, it is FOIL, right? First, outside, inside, last? No.
Oh, I see what you're saying.
Yeah.
So what does this become?
Omega squared, RE squared.
No, no. Omega squared, RE squared, but it's over RE.
So omega squared RE.
Oh, I see. Oh,
Okay. What's the last term?
U
U
U
squared,
squared
velocity
over
squared.
RE.
And what's the middle term?
2 omega.
2 omega.
RE.
Oh, U.
Oh, U. Yeah.
So, boys and girls, what is this term? What is this guy? Are you guys following me? Jacob, James, are you following?
Yeah.
Jacob, you there? Yeah.
So far, yeah.
Allison, you still there?
It's the centrifugal force.
I'm still here. My internet's just been weird.
That's okay. So that's the centrifugal or centripetal. So I'm just going to the centriforce of the Earth. As if you were standing still. Okay, so if you're standing still, that's the force you would experience. If you were zero, that's the force you would experience. Okay, so what's this force? What's this term? Isn't that just the centrifugal or centripetal force you'd experience from your own motion? As if you were, as if, not you, as if what were standing still? This is the way I like to do things. I like to say, well, what is that force? You guys remember when we did something falling from a cliff in intro to meteorology? We said there's gravity, and then there's, you have the initial, you say, if I drop from rest, I can determine how far I fell. If I am given an initial velocity, so I have the inertial component and the accelerating component. So I like to think, what is the term kind of telling me? Well, this term is the centriforce as if I were standing still. That's just from the Earth. And this is as though the Earth is standing still, and this is just from me moving on a big circle. So what the hell is this? What is this term? This. Is the Coriolis force. You can go ahead and mic yourself, James, with your hiccup.
Didn't think that was audible.
It's super. Those are your yawns, by the way. I used to have an English teacher in high school that if you audibly yawned, you'd have to stand the rest of the semester, the rest of the class period. That's the Coriolis force. Now, from a perspective of mathematics, the Coriolis force came about through this weird squaring of a term, of a sum. So when you square the sum, you get this middle term, and that is the Coriolis force. And until they did this and figured this out, people didn't know what the Coriolis force was. But I want you to see something. Which way does the Coriolis force point in this example?
Outwards.
From the, well, yeah, I mean,
From the center.
see, so apparently outward, inwardly real,
Yeah.
right? But it's along the radius of the Earth, right? So
Right.
if you imagine that the Coriolis force is the apparent force, right? Because we said that, the Coriolis is apparent, then which way would the Coriolis force be pointing to a person standing on the equator and moving on the equator? And the answer would be outward. There is a vertical Coriolis force.
In the Z direction, you mean?
In the Z direction, yeah. But imagine that I am not at the equator now. Which way does the Coriolis force point if it's over here? Do you agree that it points outward from the axis of rotation? So really, we could say outward, but what we're really saying is outward from the axis.
Axis of rotation.
Now, here's a person standing here. Right? And this force has an, if I break it into components, it has this, and it has this. That the pink plus the gold is equal to the purple. So the purple is the actual Coriolis force, but do you see that I have a vertical component and a horizontal component? And if I'm traveling to the east in a positive U direction, that force is going to be pointing to the right. So in this picture, let me go ahead and draw this again. Did you guys understand what I just said? Yes or no?
Yeah, I think I did.
This is the Coriolis force. This is the what? What would you say that gold is?
That's the centrifugal force?
No, the purple. Okay, remember the purple. The Coriolis force is a result of the Earth spinning.
Okay.
If the Earth weren't spinning, then that Coriolis force would go away. But it's also because an object is moving. So, but that force, the actual force, is always pointing in the centrifugal force of the Earth in an absolute reference frame. It's always pointing away from the axis of rotation. So here, remember this. Coriolis force. Which is apparent outward from the radius the apparent radius. And so that is the axis of rotation. It's always pointing outward from the axis of rotation. So over here, do you agree that that purple arrow is pointing outward from the axis of rotation? So what is this gold vector? Nick, how would you say what that gold vector is?
Something's making me think it's some sort of normal force, but
Well, here, it is the vertical component of the Coriolis force. I'm breaking the actual force into two components, the vertical component, and then what would the pink one be?
horizontal.
Horizontal component of the Coriolis force.
Ooh, pretty colors.
Okay, now I want you to see something. And this is going to take some serious watching. Okay, so I'm going to draw a line right here. Do you agree that that is up?
Mm-hmm.
Okay.
That is the upward. So what is this angle right? What is this angle there? Isn't that angle phi?
Phi. Yeah.
Because this angle and that angle are the
Yeah.
Okay, if that's phi, do you agree that this angle here is 90 minus phi?
Mm-hmm.
It's the complementary angle. But this is a right triangle, so what's this angle over here? That angle
Also
is
is
phi.
phi as well.
Does that make sense?
You got those, so the red and yellow are parallel.
Right. So how big is the pink vector if the purple is the actual vector? This would be the opposite of the angle of phi.
So it'd be sine theta.
So sine of phi
Or phi, duh.
times the Coriolis force is the horizontal component. Do you understand that the Coriolis force is 2 omega u sine phi? Allison, your mic's not working, but I want to hear your thoughts because you're smiling, and I know what that smile means. Your mic's not on.
You hear me now?
Now I can.
Okay, I was saying that you just blew my mind.
Isn't that so cool?
It is so cool.
I mean, it's like, oh, that's where it comes from. But we're not even close to being done. Because if I said, hey, what's the Coriolis force? You'd say 2 omega v sine phi. V meaning the velocity of any moving object. The only thing that we've shown here is that the Coriolis force is 2 omega u sine phi, because I'm traveling on latitude lines only in the zonal direction. So what if I'm traveling north and south? That derivation is completely different than this derivation. And we will show you what that is. But take a look at this. Is that cool? 2 omega u sine phi. But now you see why sine phi is in there. Because the Coriolis force is 2 omega u. That's the horizontal component. So what would the vertical component be? What would the vertical component, what would the size of this yellow vector be?
Would it be cosine?
Cosine theta.
2 omega u cosine phi. Now, at the equator, the angle is
True?
0, and what's the sine of 0?
1.
No.
0.
Oh, 0.
0, 0. So there is no horizontal Coriolis force at the equator, but is there a vertical Coriolis force?
It's 1.
Yes, it's 1,
Maximized.
right? So that's 2 omega u.
So then it's maximized at the equator for the vertical, and then when you go up to the poles, it's maximized for the horizontal.
Well, yes and no, because what's my radius? What's my apparent radius?
0.
0. So this becomes, it goes away because there's no radius. There's no motion. You're just spinning in circles. Besides, but here's the thing. If you're on the North Pole, can you even have a zonal velocity?
No.
Because where are you going?
You're going
You're not
nowhere.
going anywhere, right? You can't. As soon as you start moving someplace, you're coming off of the pole. And it's like the old joke. I said, you're standing at the North Pole and you look that way. Which way am I looking? Which way is that way? What direction?
Depends where you're sitting.
I'm standing at the North Pole. Which way is that way?
It's
South.
outward.
I'm pointing south.
Yeah.
I'm pointing south. Which way is that way?
South.
South.
So no matter where I point, when I'm standing at the North Pole, I'm pointing south. So that doesn't make any sense, right? You can't logically come up with winds. So you'd have to figure out longitude lines where you are, and then the winds are from some longitude line. So because there's north, south, east, west doesn't make any sense at the North Pole. Now, the last thing that we need to do on this is we say, well, wait a second. And I'm going to erase parts of this now. I told you Coriolis force is my favorite thing to teach because it's like, oh my God. I mean, look at the stuff that you're doing in this. This diagram is intense. Would you agree?
Yes.
Mm-hmm.
You might have to watch this a few more times and maybe draw it yourself. But isn't it cool? You're like, oh my gosh, that's why this is. And when you do that, you are now entering the realm that 1 in 1,000 people don't understand. And so I want you to think, I'm smarter than most of the world. Because I like to feel smart. Okay, so I'm gonna go here, and I'm just gonna get rid of all this stuff. Was that a yawn, James?
No, that was a exasperated sigh of enjoyment.
Okay, so now I'm over here, and I'm like, okay, wait a second. What if I'm moving at this location? I'm still moving with u, so what's my actual force? What's my absolute velocity? It's going to be omega, it's going to be omega RA, right? That's my plus u. That's my velocity. So the centric force is going to be v squared over RA, which means when we look at the total century, it's going to be omega RA plus U squared all over RA. And now we get omega squared RA plus 2 omega U, which is still the same, plus U squared over RA. Okay? So it's the same thing as it is here, it's just we're putting in RA, and remembering that RA equals cosine of the latitude. So notice that it doesn't matter for the U component in the Coriolis force, it does matter in these other guys, because this would be RE cosine phi, this would be RE cosine phi, this. But now what if I said I want to make it a vector? What can I multiply this by? Well, it's going to be omega squared, and it's going to be RA times RA over RA, making this a vector. Why is it positive?
This is pointing outward.
Because it's pointing outward. I'm talking about the apparent force, the outward appearing force. And then this is going to be plus 2 omega U RA over RA, vector, parentheses, plus U squared. Then what would this become? This becomes RA vector over what? RA squared. And that's my vector notation for the apparent centrifugal force. If I threw negative signs in front of anything, I would have the centripetal force. But a lot of times it's easier if we express it in terms of the appearing of the force. What if U was negative?
What if U was negative?
What if U was negative? And I don't want U's to be negative. Do you agree that what that would in effect do is, if you look over here, my absolute velocity is going to be less because I'm taking away a negative number here. Which means if I want to lose weight, what do I want to do when I'm at the equator? I would lose weight if I traveled west. Because if I'm traveling west, no, I lied. I would gain weight if I'm traveling west. Because I would have smaller outward force, so I would weigh more. If I were traveling eastward, I will weigh less. So if you're on a really fast flight, you could actually have less weight. Now, can you imagine a speed so fast that I balance that of gravity? I weigh nothing. Okay, what do you call that? When I travel so fast that I would weigh nothing, what would I be in?
You have like zero gravity, so it's when you're floating. So it's when you're doing like a free fall.
What kind of a motion would that be? I'd be orbiting.
Yeah.
Right? What happens when you're orbiting? If you're orbiting in space, you've got no gravity because gravity is being balanced by your big circle that you're making. Because there's gravity in space. If you're far from the Earth, it's the inverse square law. There's gravity, but you'd still fall. If you could somehow become stationary in space, you'd still be attracted to the Earth. But if you're orbiting, you don't have that. Okay, now, any questions on this before I erase all of this? Because I want to look at 2 more things today. Any questions? Okay, let us go to, I can make another circle of the Earth. Okay, and I'm just going to make something simple. Here is the center of the Earth. And here is the vector that represents what? So here's a little object on the Earth. And what does this vector represent?
Gravity.
Gravity. But I'm going to be a little bit more precise. Gravity star. Because when I'm moving on the Earth, I have less gravity. Because I have a force that's pointing which direction? Which way do I have a force pointing?
Inward. Or
Outward.
Outward from
The axis of rotation.
the axis of rotation, right? So but I'm going to make it, do you agree that that force is really small compared to gravity? But do you see that if I put that force on here, so I said, okay, this is my centripetal or centrifugal force, then what is this actually? What is that force? That's what we call effective gravity. So in other words, this is what I am experiencing. That's what I'm experiencing. So notice that gravity, because I'm on the Earth, spinning, is not truly to the center of the Earth. Now, we said that this is, gravity has a magnitude of how much? 10, or, we scale gravity to about 10 meters per second squared. This is like 10 to the minus 2. So it's really small. It's not much different. But that would give me a different direction as to where really down actually is. But what would make a difference is if I'm traveling really fast, is my Coriolis force becomes much larger. And therefore, the effect of gravity is going to be more substantial than before. So I want to take a look at those 3 terms. So what are the 3 terms that we had for the century force? We had omega squared R, A, whatever. And actually, you know what I'm going to do instead of RA? I'm going to use the RE one, so I'm going to pretend we're at the equator. Plus 2 omega U plus U squared over RE. Scale those terms. When I scale U, what do I call it? When I scale U, what do I call it? Remember?
unit vector.
Remember that the velocity of the wind scales to capital U, which is on the order of magnitude of 10 meters per second. That's usually how we do that. Now, do you agree that in the jet stream we could scale U to 100 meters per second? You could get a jet streak of 200 knots, so you'd scale it higher. Okay, what does RE scale to? It's 6 times 10 to the 6th meters, so this scales to 10 to the 7th meters. What's omega scale to? 7.29 times 10 to the minus 5th, so that scales to 10 to the minus 4th per second. So what do all of these terms scale to? What does this term scale to? This would be omega squared, so it's 10 to the minus 8th times the radius, 10 to the minus 1st. This scales to 10 to the minus 1. What does this scale to? Omega scales to 10 to the minus 4th. U scales to 10, so this is 10 to the minus 3rd. What does this scale to? 10 squared divided by 10 to the 7th. This is 10 to the minus 5th. So when I look at the scaling terms, what force is the dominant force? This is 100 times bigger than the Coriolis force. And this is 100 times smaller than the Coriolis force. But what does gravity scale to? And all of these are scaling to meters per second squared. So if I'm looking at forces in the vertical, or in other words, in the k hat direction, or you could say z. What I would say is, what forces act vertically? Gravity, Coriolis force, the centripetal force of a moving object, centrifugal force of the earth, and what else? What other force acts vertically? You're missing one. Right? The pressure gradient force. Air wants to travel from high to low pressure. So the pressure gradient force in the vertical is always going to be 1 over rho times dp dz. And if you look at that, it's going to be in meters per second squared. If I took unit mass over volume, then I become volume over mass. And mass is 1. I would go alpha dp dz. I'm going to put a negative sign in here. Why is that? How does
That's a question.
the pressure change as you go up? It gets negative. So the force is negative times a negative. But it's also in the same direction as these other forces, which was up. So all these forces are pointing up. What's the only force that points down?
Gravity.
Gravity. Okay, so when I look at this, well, how does pressure change with respect to height? What is the scale of this? What does density scale to? Density scales to about 1, doesn't it? What does the change in pressure? Do you agree that we get about, oh, I don't know, 500 millibars for 5 kilometers? 500 millibars is actually 500 hectopascals. So dP, let's say, is about 500, let's say 1,000 millibars, which is actually 10 to the 4th pascals. dz is going to be what? 10 kilometers, which is 10 to the 4th meters. 1 times 10 to the 4th divided by 10 to the 4th. And that's for this. I mean, you could say 10 to the 5th, right? For the entire atmosphere. Or you could say, if it's 500 millibars, maybe 10 to the 3rd. Right, this 10 to the 3rd, this becomes a little bit more difficult, depending on how big of the atmosphere you're actually going through. But the idea is, when I look at these forces, gravity is 10, Coriolis force is 10 to the minus 1. The centrifugal force of the moving object is 10 to the minus 5th. This is going to be 10 to the minus, oh, I'm sorry. The Coriolis force is 10 to the minus 3rd. This is 10 to the minus 1, and this is about 10. So do you agree that when I look at this, the sum of forces, that small, that small, that small, the only two forces that remain are this. So the sum of forces is about 0, which means the PGF, which points up, is balanced by gravity, and that's what hydrostatic is. And what is the hydrostatic equation? The hydrostatic equation is a vertical momentum equation scaled for the atmosphere. And when we scale it, these terms all disappear. And the reason they disappear is because we're talking about 2 orders of magnitude at least for the closest term. And that means for any equation, we can neglect those terms. For diagnostic, it's 2 orders of magnitude. For prognostic, it's only going to be 1 order of magnitude. For diagnostic, it's 1 order of magnitude different. I can get rid of it. Prognostic, 2 orders of magnitude. I said that wrong. So the hydrostatic is actually the vertical momentum equation scaled, meaning we neglect terms that are small comparatively. At least for the atmosphere. If you were setting up a rocket, you probably need to keep some of these terms because that makes the difference. For the atmosphere, we don't care. And the idea of this term, of what this term scales to, the idea is this. If gravity were too big, what would the atmosphere do? It would compress. And if it compressed, then you'd still have hydrostatic. So the atmosphere actually falls as much as it can so as to set up a pressure gradient that is going to be equal and opposite the direction from gravity. That's why you have hydrostatic environments. Now, where does hydrostatic not work? Where does the hydrostatic equation not work?
Is it in thunderstorms?
In thunderstorms. What's the force that we have to add? What do we call the force?
Abe?
No. Buoyancy.
Buoyancy.
Right? We talked about this, that we have a buoyancy force, which changes the upward. It's not balanced with the outside air. The air in the cloud is not balanced because we have buoyancy. And so we get an acceleration. So do you understand what that means? Is that if the atmosphere is in hydrostatic balance, does the atmosphere accelerate vertically?
No.
No. But in real life, does the atmosphere accelerate? In other words, does the vertical motion change? Yes. But you can't use the vertical momentum equation because the terms of gravity and height and pressure gradient are so big, they dominate everything else. And I lose all those other terms. So but they're somehow going to be important, but I got to figure out another way. And that's why we use something else to do vertical momentum. Because that's going to be a problem. So we'll be talking about that. So what we're going to do on Tuesday is we're going to go into what happens if we travel meridionally on the Earth. Because now we're talking about something completely different. Once we have the V component, we'll show you how it comes to V component, meaning the little v meridional velocity. Now it'll come to the actual velocity of any vector. So that's what we're going to do on Tuesday. And once we are done with that, I will feel like we're in a really good place. Then we will go into natural coordinates for the pressure gradient force. We've already done the continuity equation. We're going to do a couple of cool derivations of the continuity equation, Eulerian and Lagrangian. And then we're going to talk about vertical motions, which we've already talked about. The last big thing will be thermodynamic energy equation, and then we'll also have barotropic and baroclinic, and we'll talk about some large-scale circulations. So we're really into the guts of geostrophic winds coming up after Thanksgiving. And I think we have, what, 2 full weeks? I don't know about you, but I look forward to this class every single day.
Yes.
I love teaching this stuff. And it's been fun online, and you guys are good students to talk to because it's nice.
Yeah,
We try our best.
God,
Oh,
this
any last second questions?
is so much better in person still, though. But
Yeah, it is, but I like being able to draw right here because my drawings are better. I'm gonna have to get Epic Pen in my classroom and just do it on the board. So
That'll work.
yeah. Okay, guys, have a great weekend. See
Yeah.
ya.
But you too. Bye, everyone.
care.
Good luck.